Right, Assalamualaikum and good day. Welcome back to my lecture on multiple linear regression. Previously, we have looked into a simple linear regression. This is a continuation from a simple linear regression. Normally, when we analyze data, we're not going to stick on a simple linear regression, only one variable. Uh, Normally, the dependent variable will depend on multiple independent variable. So, as a introduction, what is multiple linear regression? Multiple linear regression is an estimation of linear relationship between a dependent variable and more than one independent variables or covariates. These analyses are applied in exploratory studies and some in confirmatory study. And do not also not to forget an experimental situation where experimenter can control the predictor variable. So the example of multiple linear regression also is to find relationship between predictor variables such as age, weight, and height, and the outcome variables such as PFR. PFR means peak exploratory flow rate. If we are looking into relationship of individual independent variable to PFR, it may not sound biologically as I said just now. Therefore, we need to look at the relationship when all variables are considered at the same time towards the outcome variable. So by doing this, we're going to look into the presence of confoundings and their interaction. So in multiple linear regression, it's the same as a simple linear regression, but we need to add another assumption. Um, Remember, in simple linear regression, we look into line, L-I-N-E, where linearity, independence, normality, and equality of variance. But in multiple linear regression, we're going to add another assumption, which is I, where it is stand for independence of numerical variable. So let's look at one by one. So the first assumption is the linearity of relationship between dependent variable and independent variable. The second one is statistical independence of the error. This should be settled during study design. And the homoscedasticity of the error, which is a constant variance or equality of variance. And we're going to look into the normality of the error distribution. And the last one is fit of independent numerical variable. So let's look at the type of data required for multiple linear regression. So in multiple linear regression, same as simple linear regression, for independent variable, it can be more than one independent variable. So the steps that we're going to take for performing multiple linear regression, first we're going to look into data exploration to understand the data and to try to clean the data. This is what we call as pre-processing step. And step number two, we're going to do univariable analysis, where we're going to look into a scatter plots to measure the relationship between independent variable and independent variable individually. And we were going to perform a simple linear regression for each of independent variables. And step number three, this is where we do a variable selection or feature selection. This is what we call as preliminary main effect model. And next step is going to check the interaction and multiplicity. At this stage, we call it a preliminary final model. And the last one, and the second last, where we're going to check the model assumptions. This is what we call a final model. We need to remedial measure if the problem detected, right? And step number six, we're going to do a data presentation and interpretation, right? So like dive into the demonstration of a multiple linear regression. Okay, for this example, this demonstration, we will use patient satisfaction.sav. Remember, .sav is a SPSS data type. You can get the data from this link. Don't worry, you can get the data, this note later on the material section. Right, this dataset is taken from the book titled Applied Linear Statistical Model by Nitter and Kartner, 1996. So the description of this data set is about a hospital administrator wish to study a relationship between patient satisfaction and patient age by years severity of illness, which is measured by index, and anxiety level measured by index. So remember these three independent variable is numerical variable. And the administrator randomly select 46 patients and collect the data where the larger the value means more satisfaction, increased severity of illness, and more anxiety. So the dependent variable in this data set, Y, is patient satisfaction. The first independent variable is patient age in years. Second one is severity of illness. And the third one, anxiety level. So the research question we would like to ask, is there any significant relationship between patient satisfaction and age, patient satisfaction and severity illness, and the patient satisfaction and anxiety level? So this is the example of hypothesis statement. This is for simple linear regression. For multiple linear regression, what other factors contribute to the patient satisfaction? With the presence of independent variables, all independent variables. How do the patient age, severity, illness, anxiety level collective influence patient satisfaction in the hospital? And the alternative hypothesis, there is a significant linear relationship between patient satisfaction and the combination of patient age, severity, illness, and anxiety level. Right. For the first step, we're going to do a data exploration. Before we do a data exploration, we're going to import this data into our environment. So since this data is a SPSS type of data, so we're going to use Heaven library, and we're going to use a function read underscore SAV. So we're going to import the data. So once we import the data, we would like to see, package is not installed, falling back to the URL. So let's say we install the package first, curl, right? So let's look at how we're going to be. Right, so now it's already installed and load into the library. Let's look at the first 6 observation. Right, so data 1. So let's try to see this. This is the data that we have in the data set, right? So this is the first 6 observation. So now let's try to display some descriptive statistics, right? So we're going to need to display some descriptive statistics. We're going to use maybe some value that we would like to have, which is mean, standard deviation, median, interquartile range, and then we would like to know what is the minimum value and maximum value, and then we're going to present it into a proper form. So I'm going to paste the codes that I already written from my notes, right? Right. So you can get these codes in my notes, right? But before that, you need to run, you need to call library GT summary. If you don't have the library, you need to install it first, right? GT summary. So this library will help us to present the mean descriptive statistics in a proper table, right? So let me run this one. So should get the table nicely. So it depends on your computer as well. So this is the result presentation. So let me run here so we can get the result presentation nicely. So this is the result presentation. For mean and standard deviation, patient age is 38, standard deviation is 9, median is 38, interquartile range is 14, minimum age is 22, and the maximum age is 55. So it is important for us to understand the description of the data before we proceed with the analysis, right? So next step, what we would like to do is we would like to understand the pattern or the shape or relationship by using a scatter diagram, right? So I'm going to uh, create a scatter diagram for each of independent dependent variables with dependent variable, right? So again, I will copy the codes that I already write in my notes and paste it here for to save the time. Right, so you can get the code later on in my material. So you just need to paste here. Make sure I believe you already learned how to plot the scatter diagram previously, and we have done this before in simple linear regression. Right, so let me run this one. So this is the plots that I got. So we can say that the patient satisfaction and age has having a negative relationship. Patient satisfaction and severity of illness also have a negative relationship. Anxiety level and patient satisfaction also have a negative relationship. What does it mean? It means that the more uh, older patient, the satisfaction will be decrease. The more severity of illness, the satisfaction of the patient should be decreased. Right, that is the interpretation. So we know that all of our variable towards independent variable are having negative correlation. Right, so we're going to look into a step number 2 where we're going to run for simple linear regression for each of the independent variable. Right. So what we can do manually, one by one, as we have learned in simple linear regression previously, or we can use a GT summary package to make our simple linear regression run simultaneously. So again, I'm going to copy the codes from my note and I'm going to paste it here. Right. So later on, you can see how to use this code by using GT summary. Again, I'm using a method GLM and dependent variable is Y. And I'm putting all the information statistic that I need, which is T statistic, standard error, the P value, level, global P and level, and put some title of the table. So this is how we present the result. Right? Okay, kejap. Wait, it says that we don't have this package. We need to install this package before we start with the analysis. Right, let's try again. Should be okay. Right, so ask us to install whether we would like to install package car and parameter. So we choose yes to install all and wait until the installation is complete. So now once the installation of package is complete, then we will get the summary of simple linear regression. So we can see that this is a simple linear regression, remember. Uh, there is a significant linear relationship between patient satisfaction and patient age where the p-value is less than 0.01. This is also same for severity, illness, anxiety level. And we can see the beta coefficient, crude coefficient for each simple linear regression is having a negative relationship, right? So this is quite good by using a GT summary, right? So then what we need to do, we need to check for model assumption for univariable analysis. Remember, we're not yet going into a multiple linear regression. We need to check for each simple linear regression whether all the assumption line, linearity, independence, normality, and equality of variance are met. Right. So let's check for linearity and equality of variance. Right. So again, I'm going to copy my code Right, so this is for satisfaction, patient satisfaction and age. Let's see whether the linearity and equality of variance met. So based on the scatter diagram, we can conclude that the linearity assumption is met. Right, let's look at the normality. Assumption for patient age. Right. So I'm going to use Zafiro weak tells. Right. Then I'm going to put receipt 1 and residual. So we're going to see based on the p-value, right? So we can also do by using a histogram, right? How to use histogram? Receipt 1 residual. So we should shows normality, but by using the histogram, we cannot see clearly whether the data is having a normal distribution or not because the sample size is very small. Right. So based on the statistical test using Safirovic, right, it says that the p-value is more than 0.05, means that the data is normally distributed. So next, we're going to continue for the next variable, which is patient satisfaction and severity illness. Right. So patient satisfaction and severity illness. So same function, I'm going to copy this, right? And then I'm going to paste here. What I want to do is I'm going to change this to x2 and then do for this one. Yeah, so it should be okay. So run it. Yeah, based on the severity, illness, and patient satisfaction, we can also conclude the data having a linearity assumption met and equality variance also met. Right. So again, we check normality of the satisfaction and severity illness. Right. So I'm going to use Shapiro week. Let's copy from the previous one because I'm still using the same one. Right. Receipt 1. Right. So based on the Zafiro week, it says that the data is normally distributed. And the last one, we would like to check patient satisfaction and anxiety level. Right. Again, same code I will copy from the previous one. This one is supposed to be severity illness. Right. I'm going to copy this one here. So this one should be anxiety. Right. So I forgot to change something here. This is maybe I put as I. This is A and put it I here for easy to understand later on. Okay. So this one should be AL. Then I'm going to change here also AL because I'm using the anxiety level. Right. So based on the patient satisfaction and anxiety level, we can conclude that the linearity and equality variance assumption is met. And we check for normality. Again, same procedure. We use Sapirovic. Right? Since I'm using the same receipt one, it should be no problem. Right? So based on this one, yeah, I forgot to change this one to 3. So the same thing. Right? So now the normality also. says that the normality assumption is met. Right. So next, once you already confirm that the simple linear regression is met, all the assumption for simple linear regression is met, then we're going to proceed with the variable selection. But before we proceed to variable selection, we need to make sure all our independent variable for each simple linear regression model is significant. So basically, there are three principles in variable selection. The first principle is the principle of fit of the model. Means that the higher number of variable, the model getting better and better. But this may be not be preferred principle because some of the variable may not be a significant variable. And another principle of variable selection is principle of parsimony. Means that the model with the least number of variable, but those model in the model variable in the model are significant. This is very important principle. And the last principle is biologically plausibility. Means that which the variable are proven to be significant in the literature review, but maybe it's not really significant in our model, but we need to force enter into the model because this is very important variable. So this is what we call as a preliminary main effect model, right? So to start with a variable selection, we have basically three variable selection procedure that widely used in data analytics, which is uh, stepwise analysis, stepwise selection, forward selection, and backward elimination. Right. So we need to test all these three procedure to confirm that these variables are important in the model. Right. So first we need to create an empty model. Right. So to create an empty model, I just put AEM. So to indicate that this is an empty model, y equal to 1. So this is basically empty model, right? So once we create an empty model, maybe I'm going to show you what is meaning of empty model, right? So when I click summary of EM, there are no independent variable, only intercept in the model, right? So if you look at the formula of EM, it should indicate y equal to 1 because there are no independent variable inside. So this is empty model, right? Let me bold this one as a header. And next, we're going to create another one is full model, which is all the independent variable inside the model. So let's say fm equal to lm y equal to dot. Means that we will y till the dot means that we're going to consider all others variable inside the data set, right? So then we're going to do summary fm, and I also want to show the formula of fm, right? So let me run this one. So this is all the variable inside the data set, right? And the formula is y equal to x1 plus x2 plus x3. If you notice, by using a full model, even though the simple linear regression shows that each variable are univariably significant with the patient satisfaction. However, when it comes together all the variables, you can see the x2 and x3 is not really significant, right? And then the R square is only 68%, right? So this indicate that the variable selection, one of the variable is not important, or these two variable is not important. So how to determine that? We're going to proceed with forward selection. So how to do a forward selection? So forward selection is very easy. Just I think I'll put it forward. One to be step EM. Forward start with the empty model, and we will include the variable one by one into the model. So we're going to put it as forward, right? And then scope to be until the full model lah. So we need to tell the R when to stop. So from the empty model, include one by one variables and when to stop until we reach the final model. So when you run this method, you can see that the last variable is x1, y equal to x2. So if you x1 and x3 is important. This is the last model, final model in forward selection. Means that x2 is removed from the model, right? So this is one of the method. So maybe I just put formula of forward, right? So this is a variable include in the model. So next, we're going to use backward elimination. Right, so by using backward elimination, we start with the full model, and then we're going to backward, means that we're going to remove all the variables until we found that all the variable that very important. So I'm going to put it as a backward step, right? Full model, scope, direction should be backward. Very simple. And then I'm going to put summary backward. And also I need a formula backward. Let me run this one. So based on the backward selection and backward elimination, the final model retain the variable retained in the model is x1 and x3. It's the same conclusion as in forward selection. This is also the final solution for backward elimination. So now let's try to another one, stepwise selection, right? So for stepwise selection, it's the same as forward selection juga, but it has more dynamic ways. So stepwise, step equal to the full model direction should be right. Then I need summary the stepwise, and then I also need a formula of stepwise. Right, let me run this one. So the final variable that retained into the model is same as stepwise and same as forward and backward, which is x1 and x3. So this is the final variable. So we know that from the variable selection, summary of variable selection. So we know from a variable selection, the variable that should be in the model is x1 and x3. So we can say that this is a preliminary main effect model, right? So we put it as y equal to x1 plus x3, right? And then we do a summary at pmn, right? So we should have, so this is y. Maybe I just copy this one. Yeah, I forgot to put the data later one. Okay. So based on the preliminary main effect model, we can see that x1 and x3 is important in the model. So next, what we need to do in step number 4, we need to check for two-way interaction term. So we need to check for x1 and x3. Since they only have two interaction variable, we need to check x1 multiplied with x3. So let's say we create a new variable x1, x3. This is data 1, x1, multiply with data 1, x3, right? So then I'm going to put this interaction. I just need to test whether the interaction term is important or not, right? So this is y equal to x1 plus x3 plus x1, x3. The data equal to data 1. And I'm going to put summary interaction, right? Now I should get this result. So based on the interaction term here in the model, right? So it says that the interaction term is not important. In fact, it's not important. So we no need to include the interaction term into the model. So we're going to retain the PMEM model, preliminary main effect model. So, the next step number 5, where we need to check for multicollinearity because we have two independent variable, more than one. We need to check for multicollinearity. So for multicollinearity, there are two ways to check multicollinearity. First is by using variance inflection factor, where if the variance inflection factor VIF more than 10, so we can indicate that multicollinearity exists. So if the variance inflection factor less than 10 means that the multicollinearity does not exist. Another way to check is by using tolerance, TOL. If the TOL less than 0.2 means that the multicollinearity exists. If the TOL more than 0.2 means that the multicollinearity does not exist. So how to check? So to check the multicollinearity, we need to use library MC test. So since that if we don't have the library, you need to install MC test, right? So MC test, and then we're going to use IMC Dike PMEM. So PMEM is our model, preliminary main effect model. So if you look at this one for variable x1, the VIF is less than 10. X3, the VIF also less than 10. So the tolerance is more than 0.2 for x1. The tolerance for x3 also more than 0.2. So means that there are no multicollinearity problem exists. Right. So then we can establish the final preliminary final model. So what is a preliminary final model? So the independent variable inside the model is x1 and x2. So we can put it EFM. This indicate the preliminary main effect model x1 plus x3. So where the data equal to data 1, and we put the summary PFM here. Right. Okay, so this is our preliminary final model. Right. We're going to interpret later on. So next, we're going to look at the confine of PFM. So this is the confidence interval, 95% confidence interval for x1 and x2, x3, right? So the next step, what we need to do, we need to check for the assumption of the model, right? So what are the assumptions in the model? So linearity, right? And then we have independence, and then we need to check normality, and then we need to check equality of variance, and then last is I is independent of numerical variable, right? So again, so for linearity, we're going to put using a scatter diagram, x, t, y, r, right? So this is same as equality of variance. And normal independence should be settled during study design, where we should take independent sample, and then we're going to use histogram or statistical test to check the normality. And then the independence of the numerical variable, we're going to check using a scatter diagram and xi, yr, right? So we're going to check the independence of numerical variable. If there are no pattern, means that it is independence, right? So now the first one, checking linearity and equality of variance. Right. So let me check. But before that, we need to get the residual and predicted data. So let me put resi2, right? Maybe lm, maybe data.frame. This is I put it as cbind residual equal to pfm residual, and then what I need to do next is predicted equal to pfm fitted value, right? Right. So next, I'm going to perform or construct a scatter diagram for xpyr, right? So let me copy the codes, but that I already write before, right? So you can get the codes on the learning material. Make sure you go to the right learning material to get the codes, right? So this is the predicted versus residual for linearity and equality of variance. So based on the scatter diagram, we can see that we can conclude that the assumption of linearity and equality of variance are met. Next, we're going to check normality of the residual, right? So how to check normality of the residual? We can use Sapiro-Wicks, right? Or we can plot the graph, right? Maybe I'm going to plot using a box plot this now. So you can copy the code again, right? In the learning material and see the distribution of the data, right? So if you like using a statistical test, you can use Shapiro-Wicks, Recede 2. Oops. And I need to have a residual, right? Based on the Shapiro-Wicks, the p-value is more than 0.05, means that the data is normally distributed. Right, the next step, the next assumption that we need to check is independence of numerical variable. Right, so same as scatter diagram, what we need to do is I'm going to copy this, right? My codes in my learning material, right? So I need to change this to x2. So I need to check the independent variable xi and yr residual, right? If there any pattern, it should look like no pattern, same as linearity assumption and equality of variance assumption. Right, so I'm going to plot these two graphs for H and scatter diagram for H and scatter diagram for anxiety and residual. Right, so I'm going to plot it together. Change this one to 2 again. So I should get this kind of graph. So based on the graph, we can conclude that there are no unusual relationship between independent numerical variable and residual. The form of independent numerical variable, patient age and patient anxiety level are appropriate. So they have a linear relationship with the residual. Thus, the assumption of fit of the independent variable are met. So the next step is, which is the final step, to establish the final model. So to establish the final model, we know that the final model data of variable inside the final model is x1 and x3. So I will put final should be lm y equal to x1 plus x3. So this is data 1, right? So summary, final. Then I want to have confidence interval of final, and that's all. Right. So this is the final model, right? We have from our result in R, so that the how to read the result are same as in the simple linear regression. If you can see, this is the confidence interval for each of the slope, and this is the unstandardized slope, right? Beta naught, beta 1, and beta 3. This is a standard error, this is a p-value, and this is the R square, 0.6761, and this is the ANOVA value, which is the p-value indicate the model is fit for prediction, right? So presentation of the result. So we need to combine the result that we got from a simple linear regression and multiple linear regression together to compare whether the improvement of the 95% confidence interval and then the crude confidence interval, crude regression coefficient and adjusted regression coefficient. So this is the way that I suggest you to write the presentation of the result, right? So I think that's all. You can read the learning material and try to practice on how to form a multiple linear regression using R programming. Till then, good luck and bye. Assalamualaikum.